Motor control fundamentals. Motor starters play a pivotal role in motor control by providing a safe and reliable way to start and stop electric motors. You can think of a motor starter like a light switch. When you flick the switch on, a circuit closes, which allows current to flow to the bulb. When you flick the switch off, the circuit opens, cutting power to the bulb, and the light goes off. The entire time, you're protected from being exposed to that circuit. A motor starter provides the same basic operation, except instead of a light bulb, it's controlling the start and stop of motors used in pumps, fans, blowers, conveyors, chillers, and HVAC, as well as many other processes. Motor starters also serve to protect the motor from electrical events such as overloads and undervoltage conditions. In most cases, three-phase AC induction motors and motor starters are used, which matches power transmission and utilities in our electrical grid. Though single-phase or DC motors are sometimes seen in low-voltage applications, let's take a look at a basic three-phase motor starter scheme. At a minimum, all modern starters contain a circuit breaker or fuses, contactor, and an overload protective relay. A contactor switches the power supply on or off to a motor and is designed for repetitive switching operations. Fuses or circuit breakers are used to provide short circuit protection, which clears fault conditions where a contactor otherwise cannot. An overload relay provides overload protection for the motor, ensuring the motor operates as intended and extending its lifespan. If an overload condition is detected, the contactor will open, which breaks the circuit and safely stops the motor without the need for manual intervention. The scheme shown here is for an across-the-line starter. This may also be referred to as a full-voltage starter. As the name implies, a full-voltage starter connects the motor with the power source, providing full voltage immediately to the motor upon a start command. Let's see it in action. Across-the-line starters are kind of like that light switch we talked about earlier. It will either apply full power to the motor or none at all. Cross-the-line starters are the bread and butter of the motor control world. The design is simple, cost-effective, and reliable, and therefore widely used across many applications. You can even add a second contactor with the A and C phase connections swapped to create a full-voltage reversing starter, which allows the motor to rotate in both directions. But full-voltage starting does have its drawbacks. Let's play that motor starting clip one more time. Hear that loud hum right as the motor starts? That is a high momentary surge of current, referred to as inrush current. As the motor works to overcome initial inertia and reach full speed, the inrush current that occurs is 6 to 8 times that of the motor's full load current. This spike can cause mechanical stress and strain, reducing the lifespan and reliability of the motor. Not only that, but the excess power draw from the grid can cause voltage drops on weak power systems. Reduced voltage starters evolved to help manage inrush currents and are required by some utilities to mitigate large voltage drops during startup. The early forms of reduced voltage starters include reduced voltage autotransformers and reduced voltage primary reactors. These starters utilize the tap setting of a transformer to start the motor at a reduced voltage of either 50%, 65%, or 80% of full voltage for a preset time. Once the motor ramps to full speed, the motor is connected to full line voltage through the opening and closing of contactors. Solid-state soft starters, or RVSS, emerged as a more refined approach to mitigate mechanical stress and voltage drops associated with motor starts. An RVSS provides a controlled startup of a motor by gradually increasing the voltage output. This is achieved through SCRS that allows small amounts of current throughout a time, creating a soft start. RVSS provides a greater degree of control for reduced voltage starting, which prevents motor coupling and shaft damage, rotor and winding failure, and stops drive belt squeal and breakage. Additionally, with electronic control, an RVSS offers a wide range of current limit settings, providing greater control flexibility as compared to the discrete steps of a reduced voltage auto transformer starter. For pumping processes in particular, soft starters can ramp down the voltage when a stop command is given. This avoids water hammer in pipes by allowing for a soft stop, reducing that line pressure so valves can close gently and prevent a surge wave. Let's see an RVSS in action. Hear that smooth ramp up? The inrush current was significantly reduced compared to an across-the-line starter, which in turn improves the lifespan and uptime of your motor system. It's worth noting that an RVSS only ramps speed and torque during motor startup and shutdown as the motor approaches full speed. The bypass contactor closes, which applies full-line voltage, similar to what we saw in that auto transformer. So, what if we wanted even more sophisticated control than an RVSS? That's where something like a variable frequency drive, or VFD, comes in. Let's go back to that light switch analogy. If an across-the-line starter is like a light switch, then a VFD is more like a dimmer switch. A dimmer switch allows you to fine-tune how much power is applied to the bulb, therefore giving you full control of the lighting in a room. And if you were to leave that light bulb at, say, 30% power, you would see energy savings on your bill compared to if that light was fully lit the entire time. A VFD is like a dimmer switch for your motor, allowing complete speed and torque control throughout the motor's start, stop, and run cycle. If you have a process with variable demand, then a VFD can be a much more efficient solution with significant energy savings compared to traditional starting methods. This is great for applications such as a pump that requires different flow rates or a fan that operates at different speeds depending on ambient temperature with motor control. Motors can operate safely and efficiently without the need for manual intervention. Now that we know some of the different types of motor control solutions, let's talk a little bit more about applications. Motor starters, just like motors, come in all shapes and sizes. Part of that depends on system voltage. Motor starters are available for low-voltage applications from 230 volt to 460 volt AC, such as these NEMA-sized 00 through 9 starters. Starters are often seen in applications such as rotary turntables, conveyors for material movement, and small industrial fans and blowers. Medium voltage motors are most often used when industrial processes require high horsepower loads. Switching from low voltage to medium voltage significantly reduces the current required for those high horsepower motors. For example, a 500 horsepower 480 volt motor will typically require about 550 amps at full load. That same 500 horsepower load will only require 64 amps at 4,160 volts. But in many cases, these motors are operating pumps, fans, conveyors, compressors, and even cranes and extruders. Thanks for tuning in to Electrical Engineering Channel. If you found this electrifying, give us a thumbs up, and don't forget to subscribe for more high voltage content. Until next time, stay charged and ready to transform the future.